You're running a one-person business, so you don't get the sample sizes a data team at a big company gets. Maybe you're testing 2 email subject lines on a list of 40 people, comparing upgrade rates between 2 customer segments where one of them only has 15 people in it, or wondering whether your referral customers actually convert better than the ones who found you through search. At some point, you're going to want to know if the difference you're seeing is real or just noise, and the tool most people reach for is called a chi-squared test. That instinct is fine. What usually goes wrong is that nobody tells you the test has an assumption baked into it, and small data sets break that assumption constantly. I run small businesses myself, and I make real decisions off of small numbers like these all the time. I'm not a statistician by training. I'm an operator who had to learn which tests hold up on a tiny list and which ones quietly lie to you. This is one of those places where the math has an assumption built into it, and if you don't know the assumption, you can talk yourself into believing a difference that isn't there. So what is a chi-squared test actually checking? The version most small business owners run, called a chi-squared test of independence, asks one question: are 2 categorical variables related to each other, or are they behaving like they have nothing to do with each other? Categorical just means your data falls into buckets, rather than being a continuous number. Things like opened the email versus did not open it, on the annual plan versus on the monthly plan, churned versus stayed. To run the test, you lay your counts out in a table, one variable across the rows and the other across the columns. Statisticians call this a contingency table. If the 2 variables really were unrelated, you would expect the counts in every cell to follow the overall proportions in your data. The test compares what you actually observe against what you would expect if there were no relationship at all, and it asks how far apart those 2 pictures are. There is a cousin of this test called a goodness of fit chi-squared test, which compares one set of observed counts against a theoretical distribution, like checking whether this month's traffic sources match the split you would expect from your own history. Same underlying math, different question. Most of what a small operator actually needs, comparing a test outcome or checking whether churn differs across 2 customer groups, is the independence version. So that is what I am focused on here. For every cell in your table, you calculate an expected count based on the row and column totals. Then you take the square difference between what you observed and what you expected, divide that by the expected count, and add it up across every cell in the table. That sum is your chi-squared statistic. And the bigger it is, the further your actual data sits from what independence would predict. To decide whether that number is big enough to call meaningful, you compare it against a chi-squared distribution with the right degrees of freedom. This is exactly where the trouble starts. The chi-squared distribution is a smooth, continuous approximation, but your actual data, especially with small counts, is lumpy and discrete. The approximation works fine when your numbers are large enough to smooth themselves out, and it works badly when they are not. The chi-squared statistic is only a reliable stand-in for that distribution when the expected counts in your table are large enough. Once expected counts get small, particularly under 5, the approximation gets shaky and the p-value it spits out stops being trustworthy. In practice, this usually means the plain, uncorrected test overstates how significant your result looks. You can end up staring at a p-value under 0.05 that would tell a completely different story if it had been calculated correctly. This matters because a solo operator's data is frequently exactly this kind of small. A test group of 10 or 15 people is not unusual when you are segmenting an email list or comparing 2 cohorts of early customers, like 2 versions of a landing page or 2 groups of trial users. If you run a standard chi-squared test on numbers like that, without checking your expected cell counts first, you are genuinely at risk of convincing yourself a difference is real when it sits well within the range you would expect from chance alone. The common rule of thumb, and it goes back to a statistician named William Cochrane, is that every expected cell count in a 2x2 table should be at least 5. For bigger tables, the guideline loosens a little. No more than 20% of cells should have an expected count under 5, and none should fall under 1. Notice that this is about the expected count, not the count you actually observed. So you have to do the calculation rather than just eyeball your raw numbers. It is easy to have a decent sized total sample and still fail this check. Say you are comparing free customer segments across 5 outcome categories. That is a 3x5 table with 15 cells in it, and even a sample of 100 people can leave several of those cells sitting under an expected count of 5. Think about what this looks like in a real business. You might be checking whether people who came in through a partnership convert into paying customers at a different rate than people who signed up directly, split across 3 plan tiers. That looks like plenty of data until you actually calculate the expected count in each of those cells, and you realize half of them are sitting on 4 or 5 people each. The test can still run. Your spreadsheet will still spit out a p-value, it just will not be a number you can trust yet. Let me walk through a made-up example, purely to show the mechanics, not a real result pulled from any business I run. Say you test a trial extension offer on 20 people, split into 2 groups of 10 each, and you track who upgrades. Group 1 comes back with 2 upgrades out of 10. Group 2 comes back with 5 upgrades out of 10. The expected count under no difference based on the row and column totals works out to either 3.5 or 6.5 depending on the cell, and every single one of those falls below the usual threshold of 5. Run the standard chi-squared calculation on that table and you get a statistic of roughly 1.98, which lands at a p-value around 0.16. Not significant at the usual point of 5 cutoff, but close enough that someone might be tempted to say, almost there, let's keep watching this one. Apply a small adjustment called Yates' continuity correction, which extracts 0.5 from each difference before squaring it to better match the discrete nature of real data, and the statistic drops to about 0.88, pushing the p-value out to roughly 0.35. Run Fisher's exact test instead, which works out the exact probability of your table and every table more extreme directly from the numbers instead of approximating with a curve, and you land at a p-value close to 0.35 as well. Same data, 3 different answers, and the plain uncorrected chi-squared test is the outlier of the 3. That gap is the entire reason any of this matters. If you had stopped at the uncorrected number, you would have walked away with a far more optimistic read than the data actually supports. For 2x2 tables, which cover most simple 2 variance comparisons, Fisher's exact test is the standard swap once your expected counts get small. Instead of approximating with the distribution, it works out the exact probability of the table you observed given your fixed row and column totals, and it does not lean on any large sample assumption at all, which is exactly what you need when your sample is not large. Most spreadsheet tools do not have Fisher's exact test built in the way they have a chi-squared function sitting right there, but it is a standard option in R, in Python's SciPy library, and in most statistics packages. For anything bigger than a 2x2 table, it gets harder to compute by hand, but the same software will usually offer a Fisher's exact or a simulation-based version for those too. Another practical move, if some of your categories are individually thin, is to combine them so the expected counts clear the threshold, merging trial and free into one non-paying bucket, say, as long as that merge still makes sense for the question you are actually asking. Getting the right test does not turn a small sample into a strong one. Small datasets have low statistical power, which just means a real difference can easily fail to reach significance simply because you do not have enough data yet to detect it. A result that comes back not significant on 20 people is not proof that 2 variants perform the same. It might just mean you asked a question your sample size cannot answer yet. It is also worth saying plainly, a p-value, however carefully it was calculated, only tells you about the odds of seeing your pattern by chance. It does not tell you why the pattern exists, whether it will hold up next month, or whether the difference is big enough to actually matter for your business. A statistically significant jump from 2 upgrades to 5 upgrades out of 10 is still only 3 people. Whether that is meaningful is a judgment call about your business, not something the test can hand you. If a change costs you nothing to keep running, you might act on a smaller edge than you would if acting on it means ripping out something that took real time and money to build. Before you trust a chi-squared result on a small dataset, run through a short mental checklist. Calculate your expected cell counts, not just the counts you actually observed, and check whether any of them fall under 5. If you are working with a 2x2 table and your counts are small, default to Fisher's exact test instead of the plain version. If you have more categories than you really need, consider combining the thin ones before you test, as long as the grouping still makes sense for the question. And be careful about testing a dozen small segments after the fact, looking for the one that happens to come back significant, because testing many small slices raises your odds of a false positive by chance alone, even if every individual test looks clean. Treat a not significant result as not enough evidence yet, rather than as confirmed no difference, especially with small samples. None of this makes the chi-squared test useless for a small operation. It just means the test needs the most care exactly when your data is thinnest, which is usually the moment you can least afford to be wrong about what it is telling you. The point of learning where it breaks is not to make you doubt every number you calculate, it is to make you calculate the right one before you decide anything based on it. Every one of these explainers lives in writing at dataresearchanalysiscollection.com, the whole metric library in plain English. Every metric explained in writing at dataresearchanalysiscollection.com. So go read the rest of it, and if this was useful, subscribe for the next one.